Here I'd like to go through some basic examples where we can put to use what we've seen in a previous video, where we can use either function composition, differentiation, or integration for power series in order to come up with a new power series. Specifically, the group of series that I'm going to take for granted are those Taylor series centered at 0 for the familiar functions we've seen of e to the x, sine x, cosine x, ln of 1 plus x, and 1 over 1 minus x. So with each of these examples that I have here, the idea is to look at the given function and try to figure out how we can relate it to one of those 5 that I just listed using one of those 3 operations: composition, differentiation, or anti-differentiation. So, and I should also point out the word basic here. I'm only using that to indicate that really there's just one step that gets me from one of those to what I have here. In the more advanced examples, we'll see that I can combine several of those steps to get to a new power series. So what I'm starting with here, first of all, is that I note sine of x. Of course, this is sine of x squared. But if I know the Taylor series centered at 0 for sine of x, I want to start with that. So recall that that is the sum from k equals 0 to infinity of negative 1 to the k, x to the 2k plus 1 divided by 2k plus 1 factorial. Now, if I observe that I can replace via function composition x with x squared to get sine of x squared, I can do that on both sides. So I'm noting the placement of x here, and I'm going to say that the sine of x squared is going to be the series I get when I replace x with x squared. Now, it's best to get into the habit of simplifying this, and what I mean by that is that I can write this by taking, whoops, this should be a negative up here. I have negative 1 to the k, and the denominator I have 2k plus 1 factorial. But I can rewrite x squared raised to the 2k plus 1 as x to the 4k plus 2. And that's more simplified. And in particular, not only is that nicer, we'll see that when we do have a situation where there's more than one step to get my new Taylor series, simplifying along the way will prevent us from making some unnecessary mistakes. So here's an example of function composition. If I look at 1 over 1 plus x squared, then what we can think about here is taking the derivative of arctangent of x. I should have added that to my list of known functions in the beginning. So the 6th function we know the Taylor series centered at 0 for is arctangent of x. And if you recall, that Taylor series is the sum from 0 to infinity, negative 1 to the k, x to the 2k plus 1 divided by 2k plus 1. So no factorial here for the arctangent. And what I want to focus on is that we said that we simply need to differentiate the part that involves x within that sum. So doing so, leave that there, we're going to have negative 1 to the k, and of course I still have my 2k plus 1 in the bottom. When I take the derivative of x to the 2k plus 1, that brings down a 2k plus 1 and leaves me now with x to the 2k. And let me pause for a moment and look at what we can say about where this starts. What I want to note is that the original series, if we were to write out the terms, would be, so starting at k equals 0, we'd have x minus x squared over, no, excuse me, x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, etc. So what I want to think about in each of these instances is what happens to these terms. And the thing I really want to focus on is the x term. That's going to help me figure out this here. Well, that was in the original part. That's the term we got from k equals 0. If I take now the derivative of x, of course I get 1. That's going to be the k equals 0 term in my new series. It did not vanish, so I do not change the starting value of k. If, on the other hand, we had differentiated a series whose first term was, say, 1, then taking the derivative of 1 would be 0, and I'd have to then start my new series at k equals 1. So every time I'm taking the derivative, I'm really just checking what the first term of the original power series was in order to determine whether or not I keep the index starting at the same value or bump it up by 1. And then the last thing I'll point out here is that we can simplify this. These 2k plus 1s cancel, and I get k equals 0 to infinity, negative 1 to the k, x to the 2k. That's my final answer here. And I'll also point out that that's not the only way we could have come to this conclusion. You could also have used the 1 over 1 minus x function, because this is 1 over 1 minus negative x squared. So we could have used function composition to get to this same point. And then finally, suppose I wanted to find the antiderivative of natural log of 1 plus x. So taking the known series, so we have a Taylor series for the natural log of 1 plus x. If I want to find the antiderivative of natural log, I don't actually have to antidifferentiate. This is saying find the power series representation. So again, I'm going to replace the natural log of 1 plus x with its power series representation. And again, focus on the fact that I'm really just going to antidifferentiate the x term there. In doing so, the negative 1 to the k plus 1 and the k don't change because those are independent of x. But x to the k becomes x to the k plus 1, and we divide by k plus 1. The other thing you should recall here is that this is an indefinite integral, and that means that we tack on a plus c because of that. So this would be my antiderivative. So this just shows us how we use those operations just in kind of one step to get to where we need to go, with the original Taylor series being something that we know offhand. And like I said, that's why those 6 familiar ones are going to be so useful. And then the question becomes, how can I relate what I have here to one of those functions? I will point out it's very important that the center here is 0. So this, what we've done here, if I had asked for the Taylor series centered anywhere else, knowing what, say, sine of x is at 0, if I had to find sine of x squared at, say, pi, that doesn't help me at all, because we'd have to completely reevaluate what the coefficients would be. So this is only useful when the center remains the same for all of these. So let's skip over the next one. And what I want to also consider here is, instead of just focusing on one of those operations, another thing that we can do relatively easily when we're talking about power series is multiply and divide by powers of x. So let's assume we have the same goal here. Find a series representation, or the Taylor series centered at 0. In this case, for x squared times cosine of x. Again, I'm going to start with the fact that I have a power series representation for cosine at 0. That's my Taylor series, negative 1 to the k, x to the 2k, over 2k factorial. And I'm replacing cosine of x with that. Now, if I have the x squared outside, again, notice there's no interference with k. This is just constant with respect to k, so I can bring it in and outside of the sum. So what I want to do is collect it with the x to the 2k in there. So what happens is that the x to the 2k now becomes x to the 2k plus 2 by bringing in that x squared term. So this would be, consequently, the Taylor series for x squared times cosine of x. Dividing by x is very similar. Here, you could think about sine of x. Again, let's write what that Taylor series is. Here we have that, and we're going to divide by x. Well, dividing by x, in some sense, you can think of this as multiplying by x to the minus 1, but however you think about it, there's x's inside and this 1 over x outside. So again, we want to combine those terms. The negative 1 to the k and the 2k plus 1 factorial are unaffected by this. But if I divide x to the 2k plus 1 by x, that's just going to leave me with x to the 2k. So anytime we're dealing with either multiplying or dividing by powers of x, that's something that we can quickly adjust power series representation by adjusting the power on x that we see within the sum. In the next video, I'm going to look at some more examples that combine several of these things we've seen here to get to a new Taylor series.